Okay, wonderful. So as usual, I didn't follow what I promised. And that means I found some very interesting things going on right now and decided to talk about this. So I'm changing the format a little bit. Usually we have, as you can see, we have some theory and then approaches to practical uh, aspects. And we have not been to practical aspects for quite a while. Yeah, we were running notebooks, Qiskit notebooks, but rather than saying what we will not do, I'll tell you what we will do. Okay, so first of all, right now, there is an IBM Qiskit Summer of Learning going on. And those guys meet once every year in the summer, and they record lots of interesting videos. They are all members of the Qiskit community, that most of them work for IBM. And I will show you some of that stuff. And then I'll show you some of the people and some of what they talk about, and that's the plan, and then we will discuss it. So for that, I really need to stop sharing for a second and then share it again, but this time with the sound. So if we watch some video, because a few minutes of some of them are worth it, then it's you can all hear it. Okay, that's the plan. Now, in that plan, maybe I should be consistent and just exactly follow the outline, even though it's not exactly, it's first practice and then theory, it's not really so much practice. It is rather, let's look at the event. Okay, now the link for that is all here, right here. So you don't need to record anything. I don't have to give you those links. If only you're looking at that particular file, then you have it all. And I see those pictures tell me that you are looking. So first of all, that's 2023 2-week intensive summer program. And I'm not sure why they call it, I don't see any organization. I don't see people coming to school and learning and going home then. And because it's all online, right? And then you can watch them when it's done anyway. But what they're doing is very interesting because they said this is the 4th summer school, and that's this time they want to go back to basic. Well, perfect for us beginners, and that's what they do. So I prepared one of the lectures, just the beginning of that to show you what they will talk about. Now, could be that you go to the school and watch. Then I invite you to share your impressions and be part of it. I'm telling very interesting things if you have not heard them, but if you have, that's useful for us to tell exactly what you're doing. Now, the next one is this. This is Olivia. So before we go with Olivia, let's click there and let's open. But stop.
So Bespoke Post,
Oh,
they just send you a cool box every month.
Whoa.
The value of every box is at least around $70, if not more. It's a pretty smoking deal. You're getting a month.
Okay, at least I skipped the ad.
Hi, my name is Olivia Lanes, and I'm giving the next lecture in the Qiskit Global Summer School. Today's lesson is going to be on quantum computing hardware.
Okay, I apologize for the ads. In another account, I have kill the ads, but here no. All right, that's Olivia. That's the one who is Qiskit advocate all over. She is world famous, and she is the one who showed all the pictures. So if the books. So if you remember, we started with how do we learn quantum computing here. We went to the blog. Okay, and last time you guys asked So how do you start learning? There was this blog post that I showed you, and we went through that. That's not new. But these books are really coming from her. If you go and start reading about quantum computing on Amazon, you will find all kind of popular literature. But, well, let's put it this way, real books you will not find. And that's what she advertises as real, that maybe 10 or 20 years old. But in quantum computing, as we know, that doesn't mean anything. So we went through this, and I promised to add something else. And that was this, how to talk quantum computing to a teenager. Let me just show the beginning, because I do not think that we ever did it. Last time I said I want to find it, and I left it at that. And that's the talk. Now, the link is found there on the books blog, but I think I will do well if I copy this. I apologize for all those multiple browsers. And I will do well if I put it here. That's our class. That's additional useful link. Let's put it right here in the books. And that's the funny picture. Now, the funny picture disappeared. Here. And just the beginning of it, that it starts that talk with obvious implications, but that talk is about quantum computing. The boy is very excited about quantum computing and hides his book on quantum computing. And the mother says, oh, he's growing so fast, and so on. From there, you will start enjoying it, how they talk about this, and what that is what the particles do when nobody watches them. That's the biggest discovery. Okay, that came from Olivia. That's why I showed this to you. So let's go back. And that person is, for a change, talking about the hardware. They avoided talking about the hardware, and that is because, as you remember, quantum computing is very complex. There are at least 3 levels you can approach it. And one of the level is the hardware. I want to imagine what's really going on. But most programmers and most mathematicians prefer to never even think about hardware. They say that's abstracted from me. I only deal on the level of the code. I don't care what really happens in there. Well, you get the feeling that something is missing in your worldview, because really the hardware exists, and that's what makes the computer possible. Okay, in any case, I will give it a few minutes.
Hardware and superconducting circuits. So to outline what we are going to cover today, we are going to talk about what a real qubit is for probably the first time in the 2-week series of lectures. Then we're going to talk about atoms and artificial atoms, also known as superconducting qubits, and we're going to talk about why they are sometimes called artificial atoms. We will then go into the DiVincenzo criteria, which is the criteria that was set forth that we have to have in order to say we have built a universal quantum computer. We are then going to talk a little bit about classical circuits so that we can compare and contrast their components to the quantum circuits that we're going to be building, and the Josephson junction as the most crucial element of those circuits. And then lastly, we're going to talk about how to control and measure a transmon qubit, which is the type of qubit that IBM builds all of its quantum hardware from. So the motivation of today's lecture is basically to understand what is in the golden chandelier. This is the cryostat, the dilution refrigerator, that houses basically all of the cryogenic components, all of the quantum components, the cables, the amplifiers, everything that we actually need in order to read out the quantum computer at cryogenic temperatures, not including the room temperature controls, and the quantum processor itself. Like I said, this is a cryogenic machine. It's made up of many different stages, so you can see the different stages, the different levels, where all of the wires are connecting each plate, each different level to one another. And it's gradually getting colder. At the top, it starts out at room temperature, and then at the bottom, it hits temperatures of about 15 millikelvin, which is colder than outer space. It's insanely cold. And we do this through a mixture of a combination of helium-3 and helium-4. And like I said, all this quantum stuff is kept at insanely cold temperatures all the way at the bottom here in the canister, which you can't see in this picture because it's all canned up for experimentation purposes. And we're going to go into what's in it and how to build up these devices.
I'm coming to the next picture.
So now let's talk about the DiVincenzo criteria. As I mentioned, this was coming earlier.
Okay. Oops.
Good morning, everyone, and welcome to today's lecture of the Qiskit Global Summer School. I am your host and lecturer, Zlatko Minev.
I didn't really mean that one, not yet. So what I found wonderful, first of all, they're all great lecturers. But what I found wonderful about this Olivia's lecture, it's not so much that she turned to physical hardware, it's that it is very dense. It's an amazing amount of materials. Now, I personally like to utilize the time. For example, maybe I'm walking, or maybe I'm exercising. I like to listen to such things. And I started listening to Olivia, but I very soon realized that it's a waste of time. I'm not getting anything if I'm not looking. You saw how condensed it is. Well, you're missing all of it. The pictures are very important. So that was the first discovery that I made, and here are the links. And I'm almost sure that you will listen to that because it's unbelievably useful. Now, that was the funny pictures, how to talk about quantum computing to a teenager, which is very nice. But the next one is this. It's what they really do. They, meaning the PhDs, and really do, that means do it on Friday at 11 Central. In other words, what they really do right now. Well, this is what they do. Oh, no more ads.
And good morning to you, everyone.
All right. So that is about the most advanced quantum computing stuff. Now, I watch it every time so that I just know what they're about, but usually that is very deep. Like this one is classical shadow tomography. It's not even easy to figure out what that is about. But I wanted to show you that there are, first of all, elementary educational schools at IBM, that one with Olivia and other people. And then there are advanced seminars every week with these guys. So you can subscribe and you can do that. That is what I wanted to show you. Okay, I'm closing that because I'm loading you with a lot of wonderful, deep information. If some people say it's kind of boring and it's not interesting and it's not enough challenge, well, here there's enough challenge. Now, the last thing that I will show you today is yet another guy, a wonderful lecturer. Here he is.
Welcome to Understanding Quantum Information and Computation.
Okay, now that guy is called John Watrous. Watrous, almost like walrus, but a little bit different spelling. And he is a mathematician. He definitely appeals to the crowd who is into math, understanding of things. He never talks about hardware. He was a professor, I think, at Michigan University or some other North state. And then he was at IBM. He is at IBM. Oh, Watrous, that's his real name. He is main thing is teaching at the IBM, and he is there for maybe a second year. Now, some people who like the math approach find it just right, and there are many excited people here with 23K subscribers, but that's to all of Qiskit. That's what I wanted to show. Now, however, I listened to him quite a lot already. I definitely recommend it, but that is only if you are into such things as, let's jump.
And intuitive terms. Mathematically speaking, the set of classical states is just a finite set. And of course,
there you are, right? You said it. So first of all, a classical information is bits. Easy enough. But then right away, by the way, the classical information is just a set of finite states. That's already mathematical enough. Okay, now with this wonderful person, what I discovered, he is on the same Qiskit library. What I discovered is that he has a book. That's new. Now let's go and check. He has a book, The Theory of Quantum Computation by John Waters. And if you are bothered by the fact that Mike and Ike, our famous Mike and Ike book. So let's go first of all back to Mike and Ike. Where is it? But I do want to show that picture. Okay, I'm not showing this picture, but that's good enough. But this wonderful classical Mike and Ike book is 23 years old, and it's still as good as gold. But if you're bothered by that, if you want something newer, well, here's the 2018 book. I think that I found it. It wasn't hard. There you are. Okay, and that's the book, University of Waterloo. That was probably big before he came to IBM. Yeah, 2018. So I looked at it and I'm offering you the first look at what he's talking about. But as you would expect, and I told you already his secret, it's mathematical preliminaries just to start. So we're going with the necessary math. If that is your approach, then you will love it. But if you start with something like there are electrons or that's an international competition, then he's not talking about that. Now, what is he talking about? First of all, math that you need to even understand. But the good part of it, if you do this, then you really do the right thing. You understand what you are doing, and then you stand a chance. I don't think anybody stands a chance if he or she doesn't really understand all aspects. There, I said it, right? I think that it's nice if some area gives you more pleasure than the others, but I don't think you can do something like serious enough. And by serious enough, I don't mean to be a researcher necessarily, but I mean more than, let's put it, kitchen talk interest, and more than, look, I'm just a manager here. No, that doesn't work. That's what I think. So it's useful, and I would put it on the bookshelf and or a link, and have it on my reading list in addition to all the others. But what can you do? That's quantum mechanics for you. So first of all, he says that's the math you need. Then he says, now what we're doing really is quantum information, and that is based, of course, on quantum physics, but he doesn't go on that level. He goes on the level of above the hardware, and then immediately he starts using this knowledge. Now we're talking about quantum information. So there are channels, there are states, they can communicate to each other, quantum entropy, entanglement, and the famous teleportation. I really love the term teleportation because it really means that there is a way to teleport yourself, except that you would have to disassemble every atom and send it somewhere else. Okay, I wanted to show this wonderful book and I did it. I showed the lecture. I also wanted to do it. And right now we are right here and I don't have any specific practical labs for you to click upon. Okay, so let me do this. Let me close that. Let me stop sharing the screen. And kind of let me stop talking and let me be silent for a short time so that you can ask your questions, express your desires.
Have they done any research around teleportation that looks promising?
Yes, they use teleportation. It's part of the algorithm, but no more promising than teleporting that particular uh, particle, that photon or electron, not people. Sorry to say about that.
Yeah,
The
I heard that.
interesting, yeah.
I heard that the Chinese did an experiment. They had some electrons down on the ground, which they entangle with a beam that they shot up to a satellite, and then they collected them at the satellite, and they varied the ones on the ground, and then the ones in the satellite responded in kind because they were coupled, right? Did you hear about
That's
that?
no, I haven't heard about this. So maybe
This
you
is
give us
over a year ago. Yeah.
a link, right? It would be nice. Okay, if you give us a link, we'll look at it. But keep in mind, it's real teleportation in the sense that it's not a copying. There is a theory, a theorem that you are not allowed and cannot copy a particle. So you end up with real teleportation where the original is not here anymore, but the teleported particle is real. So show us this article about how Chinese teleported somebody to the moon or
No, they just
the
shot
spaceship.
electron beams. They shot electron
Beings,
beams that
okay.
were coupled. They were received by a satellite, which of course was very far away, relatively speaking. And they then found that there were sensors in the satellite that confirmed that when they influenced the electrons on the ground that were
Well,
coupled,
that's
ones
it. If you
responded in the
remember where
satellite.
it was, would be great. Besides, yesterday's Nobel Prize was for work on lasers with very short beam. So I wonder if you can use that in quantum computing and teleportation. I have not looked at it anymore. Okay, guys, but we usually do something practical. So let me do this. Let's do something practical. It's not
What's a
not
laser with a short beam? A pulsed laser? What do you mean a short beam?
well. Let's share the screen. It's the Nobel Prize that came out yesterday. But since I usually see, well, since my wife sends me the news from the reporters, and I don't read news from the reporters because it's just click SEO, then I haven't looked at it. But now that I realized I should, and our agreement is that when she sends me a report on news, if I don't find it interesting, then I find a lot alternative that is interesting. So it should be Nobel Prize 23 for that's probably in physics, but it should be about lasers. Yes. Oh, that was an interesting story, by the way. One of these guys donated all his money to help Ukraine and to help people in Ukraine. That's this guy. But now let's go, what was the Nobel Prize about? Ultra fast laser tracker electrons. I think that's it. I can't do it now, but I'll make a note and I will read about this. So maybe we should look at it next time and also figure out, does it have anything to do with quantum computing? I think that would make sense. So let us put it there. Well, let's save it. Okay, and let's put it there. So that's for the next one. All right, but that's one thing. What I was planning to do is, well, let's bring up some notebook. That will be fun and see if it works and do some kind of quantum computation so that nobody will say that we just blah blah and don't do anything real. Okay, and that is found in my case right here. Projects. It's quantum computing, right? It's quantum computing labs here. And I need to switch to quantum computing environment, which is on the environment list. There are all my environments. And that one is Qiskit. That's what it's called. Okay. So therefore, conda activate Qiskit. And then I can start. Okay. I can say Jupyter Lab and see what we can do in quantum computing lab today. After all this talk, we see how diverse the knowledge is. It can be photons, electrons, very cold temperatures, but it can be this, representing the qubit states. So out of all of these labs, they all come from the beginning. Does anything really beckon, does really anything stand up so that we can try to do that lab? Anything? Okay, I'll choose something. Maybe representing qubit states. The exciting part about this is you never know if it'll work today or no. But that is the lab representing qubit states, right? We'll start, we'll see how it works and what does it give us. So if you're familiar with the notebooks, then the way to run the code, these are comments and this is the code down below. The way to run it is by either clicking here on run or holding down the shift key and hitting return. Now we come to the real code where we import the libraries, and that's where we verify that indeed libraries are installed. That's why I switched to Conda environment that's called Qiskit. And now I'm trying to get them. And let's see. It got them. So it got these libraries that have to do with quantum computing. Of course, we remember that these are not the only libraries that do quantum computing, not the only ones in the world. Google has their own, and at least Intel has their own. And I haven't even come to them, haven't tried them. But Qiskit is big enough. Okay, then the next step that we do is create a simplest quantum circuit with just one bit, one quantum bit, one qubit. And that's all we do, just create one. But then we'll do something interesting. We will create a circuit with one qubit, and we will initialize it to a 0, 1 state, which means that we give it we act on bit number 0 and we set it to state number 1. That's what we do, and the place where we do it is right here. Okay, and then it will be interesting to plot it. So you see it initialized it, and I don't think anything happened as yet. We say that's what we will do, but we're not running it as yet. And then therefore is represented like this. What you're asking me to do is this, but I'm not doing it yet. The next step is, well, let's do it. For that, we need to either send it to an IBM computer on the back end or use a simulator. And you would imagine that, of course, we would use a simulator. But if you do use the real one, it works. Of course, it's a very small one, so no fun. The interesting thing is that there are a few thousand people in the queue. And if you submit it, it will tell you, well, your job is number 1500. And then you will wait. In my experience, I waited for half an hour to an hour. So it looks very much like a mainframe feeling, except that now there's a very different mainframe inside. But we're doing a simulator. It works on this machine, works very fast. And now that simulator is ready, I'll be able to run. So here we're doing everything again. We're creating another circuit, initializing it, probably to combine everything in one place. But now we do the simulation and we run it. And we get a state vector that is real. It has probabilities, it has amplitude. And out of that, we can do something else. We can measure and draw. By the way, that picture looks different from when you would run it in another place like Colab, and that's the least spectacular way on this Mac. But it does mean the same thing every time. So that's what we've done. We ran it, we measured it, and that's not very useful, very exciting algorithm, but at least it's running, right? And then you can do already some graphics, which shows you that every time you run it, you get this result. What the result? 1, okay? Result 1. How many times you run it? 1024. That's the default. And then it shows you what was the result every time, and the result was the same. If it was not the same, then you would have a chart of how many times you got this, how many times you got that. But in that case, you get the same result every time. And now we're going to go into more or less realistic states. So if we print that result, it will be some, in this case, I think we're using the what's called the Bell state. So it is in between 0 and 1. But we remember that there's much more to be said about this, because yes, it is in between 0 and 1, but for the entangled particles, it's not exactly 2 either, okay? That's what this, okay, and finally it broke, very nice. That is what this lab does. And if you are interested in how to run all of that, then it is found right here. It's found right here. Quantum computing labs. They are open here. And the one that we particularly ran was this one. Right? So I'll give that link on our seminar. And my goal today was just not limit ourselves to talking about exciting news. That's why I showed the lab. But on the other hand, my goal was not really to also do any serious labs. So I'll put this link here because my major thing was very interesting and exciting things that happen here at the summer school, the Qiskit summer school, at the wonderful lecturers. And if you want to do something and click around, you'll go to this lab on GitHub. Now, if you are not set up, then you can do one of the two. You can upload it to Colab, okay? That's one way. Or you can look at the whole lab. So what I showed you, I pointed to a specific one, okay? But what you could do is go to the very beginning here and look at setup, do the setup, and it explains how exactly you do it. All right, this is the second time that I'm going to stop and not share anything. And if you have any comments, any desires for the next time, that's wonderful, give them to me. And if you don't, well, you'll have to rely on me what will strike my fancy for the next week. But it will definitely be something interesting and exciting because as you see, the field is just brimming with all the interesting and exciting stuff. All right, so be well and write to me if you have any additional questions. And I wish you a great weekend and a wonderful fall. Yes? Well, thank you very much and goodbye.
Thank you. Bye-bye.
Thank you. Goodbye.